Welcome to my talk. My name is Zhenyao Mo, and I'm working for Google. Currently, I'm on the Chrome GPU team. For the past 2.5 years, I'm spending my most efforts implementing WebGL for Chrome. So before I start, I want to show you some magic of what WebGL can do in just simply a few lines. So can you see this is a very shiny teapot in a 3D. This is in WebGL. So I want to make it a cartoon style. And it only takes you 3 lines to do that. So this is the source code. I already added the lines. Now I just need to uncomment those lines and save. See, so this is cartoon style, only 5 lines. And with original fixed pipeline, it takes way more effort to achieve that. But with shaders, that's what you can do. Processing is per pixel. And with this, you can easily have all kind of very fun, very exciting, or even weird effects on your screen. And that's what WebGL can offer with the current pipeline, current design. So I'll explain to you later what those a few lines do. But now let's start from the beginning. So feel free to interrupt me if you don't understand anything. So first, I want to explain what is WebGL. In a few words, WebGL is 3D graphics library for the web. So it's based on OpenGL ES 2.0 standard. Why is that? Because then we can run the same, provide the same API on desktop, on laptop, and also on mobile devices. Because OpenGL ES 2.0 is widely implemented in most mobile devices. And this is a little bit different from any other JavaScript standards because it's 2 language. It's combining of JavaScript interface and also shading language, which is the language for GPU. But it's not as scary as it sounds. I'll show you how shaders can be very simple and easy to understand and easy to write. So WebGL right now, it's implemented in Firefox, Chrome, Opera, and it's also, because Chrome and the Safari share the WebKit, so it's also implemented in WebKit. So in Safari, if you turn on the switch, then you also have WebKit, but it's not on by default. The only main browser that's not implementing WebGL is Microsoft IE. But again, we have a solution for that. If you install Google Chrome Frame, which is a plugin for IE, then the browser will look like IE, but all the rendering is done by Chrome. So then you can have all the cool features Chrome provide, including WebGL. So that's our solution. Basically, with this Chrome Frame in place, then our main browsers should have WebGL available. But again, because it's a graphics library, so it also depends on your graphics hardware. If you have a really old GPU, have tons of bugs in your drivers, then it's not only unpleasant to run some graphics content on it because what you see is not what you expect. It can be really like dark triangles suddenly popping out of the geometry, those kind of weird things. But also it can be unsafe because there might be security bugs in the driver. So we try to work around many of those, but some of them just not possible. So what our solution is, we blacklist some really bad drivers and GPUs. And for right now, I just get this data yesterday for today's talk. And this is purely, I get the data from Chrome, but I assume Firefox should have about the same percentage. So on Windows right now, we have 68% of users that have WebGL. And the rest 30%, mostly they are XP users. They have really old hardware, really old driver. For example, like my dad and my mom, you cannot expect them to update their graphics drivers. It's way too complicated for them. So they basically cannot have WebGL. But again, we provide another solution. We provide a software renderer, which is called Swift Shader. So if your hardware GPU driver is pretty bad, but then you can download this optional Swift Shader, then you can have WebGL. Only that the frame rate may not be that great. But for many applications, they don't require a 60 frames per second frame rate. Then you can still enjoy WebGL on a really old computer with old GPUs. And on Mac, we almost have all Macs. And recently, we have some regressions on Mac, and the 10.7.3, they have many bugs in their drivers. But we are working with Apple try to solve that quickly. And but before, basically on Mac, you can safely run WebGL, no problem. And on Linux, we currently only have 34%. But we are working hardly with NVIDIA, with Intel, and with AMD. So I think their good drivers are all in line. They are going to be released pretty soon. And if you grab those new drivers, then you can have WebGL. So basically, the good news is I think just in a few months, like you can have like maybe 90% of the users of the whole web will have WebGL. That's the good part. So now I want to explain a little bit about how GPU works.
So the mobile users are excluded, or?
This data doesn't count mobile users because currently very few browsers provide WebGL, or WebGL is good enough on the mobile. But that's, I think, basically it's the hardware needs to catching up.
Also, Chrome doesn't support WebGL.
Yeah, Chrome doesn't support WebGL at the moment on mobile. So this is what the general, a very rough illustration of how the GPU pipeline works. Basically, you input data streams to, basically there are two parts. One is the Vertex Shader, which is basically processing data on a per vertex basis. Then the Fragment Shader is processing the data on a per pixel basis. So you input the data into the Vertex Shader. Those data is like vertex properties, like their coordinates, their normals, their texture coordinates, or their colors. Those vertex attributes you input to the Vertex Shader, then do some computation, then output something, output some data. Those output will be the input of the Fragment Shader. Then Fragment Shader will, again, processing those data, and what they will output is the color for each pixel. Then that's what you'll see on the screen. And that's how the GPU works. And the Vertex Shader and the Fragment Shader, the one good thing about them is they can run in parallel pretty fast. So it can process like hundreds, thousands, tens of thousands, even millions of vertex pixels at the same time. So that gives you a high performance. So shaders, what are shaders? Shaders are programs running on GPU. So usually we write programs that's running on CPU, but shaders are programs for GPU, and they're pretty small, and they're stateless. That means they run for each pixel independent of each other, and they don't save state, so each one is independent. And then they have a high degree of parallelism. That's what makes the GPU a great processor. And Vertex, as I said, Vertex Shader applies to each vertex, and Fragment Shader applies to each pixel. Because we know the output of Vertex Shader is the input of Fragment Shader. So output of vertex shader is per vertex. And then the GPU will automatically figure out, like, for a given pixel, if a fragment shader is running for 1 pixel, then basically it will automatically figure out which vertices will affect this pixel. Basically, this pixel is belong to which triangle. Then it will automatically do blending of all the output of the corresponding vertices, then get the data, then do some computation, then will output the color of that pixel. So now I'm going to walk you through a concrete example of a very simple WebGL example, which will basically draw a color triangle on the screen using WebGL. And this is the link for the original demo. So this is a very simple vertex shader looks like. It's only a few lines. So first, this you can see it starts with attribute. And that means those are the input stream. So basically, these give you the attributes of each vertex. They can be color, they can be position, they can be normal, they can be texture coordinates. That's the attribute of each vertex. And this, you can see, those variables start with varying. That means those will be the output of the vertex shader, but then they will be the input of the fragment shader. They will be the input of the next stage in the pipeline. And the code is very simple. It's basically, because this attribute position is the input, so each vertex we already know the position, and here we don't apply any transformation, so there's no matrix operation. So we basically just take x, y, z as it is, and the w is just 1.0. So this will be the final position of each vertex. And this GL position is the reserved keyword. So basically, when you assign value to this property, that's the final position of that vertex. And then we assign the color, input the color directly to the V color, which will be passing down to the next stage. So this is what a simple fragment shader looks like. So first, you need to declare the precision of the operation of the variable you want to operate on. So basically here I say precision median p float. That means all the float will use median precision. But that can vary from device to device. But the spec will specify what's the minimum requirement for medium or for high. Then at least you can expect some of the, you can have some guarantee of how precise the data can be. Then you can see this again. You see this in the vertex shader, but now you see it here again because the output of the vertex shader will be the input of the fragment shader. So you get the color from vertex shader, then basically you just assign the color to the final as the final color of the fragment shader. But here you need to know that vertex shader is per vertex, and here is per pixel. So basically, before you even enter here, the GPU pipeline already automatically do the blending. So if you have select a pixel inside a triangle, then it will take into consideration the three vertices and their colors. Then depending on the position of the pixel to the position of the three vertices, it will do some linear combination. Then that's the input V color you get. It's not directly from vertex shader, but a blending of related vertices. Then you can directly assign the color to this fragment color. And if you just want pure red on your screen, then you can just say GL frag color is red, like 100. Then you get the whole screen will just be red. It's as simple as that. No magic here. But you can also do some very complicated things here to get some very cool effects. So here are some difference between, basically you can calculate the final color. Like in previous example, we calculated the color in the vertex shader, then the color just passing down to the fragment shader. But sometimes we can calculate the color on a per pixel basis. So this gives you a more accurate color model. As you can see from the two examples, the left is rendered, basically compute the color on a per vertex basis, then just do some interpolation. And the second is compute the color on the right is compute the color on a per pixel basis. So you can see you see the right side you don't have the highlights, but the right side you have because it's a finer model because per pixel. In most cases, a triangle is more than 1 pixel. So if you compute the color on a per pixel basis, it's more accurate. So give you more details. And that's a choice sometimes you want to make, whether how good the rendering you want it to be. So then this is just regular JavaScript. So you can put the shader source code as a script, and then you can give it some type. And type is basically, as far as it's different from text, then that's fine. You can just specify anything. But the one thing is you need to separate. Basically, you need to let the code know, like give it ID, for example. Then you can know which this text is about. For here, we only have two. So we say one is VS, that's vertex shader. One is FS. So later you can use this ID or use the type. Then you can know which is which. So now the first step to build a WebGL program is to get a WebGL context. So that's very simple. You have a canvas object in your HTML file. Then you use this canvas to get a context. And what kind of context? Then it's a string you pass down. And here we want WebGL, so we say experimental WebGL, because we can only claim WebGL once it's fully passing the conformance test. So right now we use the word experimental WebGL. But once we are fully spec conformant, then you can just say get context WebGL. Then you will have WebGL context to do all the stuff WebGL allows you to do. But here you can also get a now. That's basically if the driver is blacklisted, then you will get a now. Then you can pop up a warning box to your user that upgrade your driver, get a better GPU, whatever you want to do with that. And for Canvas, you can also get a 2D context. So basically, if you say get context 2D, that will give you a 2D context. Then you can do tons of like draw a line, draw a circle, those kind of 2D operation. So now we have a GL context, and we have the OpenGL source embedded in the HTML file. So now we need to load the shader, because basically we need to let the GPU know which program you are supposed to run. So for each GPU program, they consist of one fragment shader and one vertex shader. So this is the code, how you upload the shader. You get the shader. So this is basically, you get the element by ID, the ID, and here we basically use the type to distinguish whether it's a vertex shader or a fragment shader. But for our example, you can also use the ID, because one ID is VS, another ID is FS. So basically, they are good enough to tell you which one is which. Then you create a shader based on the type, whether it's a vertex shader or a fragment shader. Then this shader source is basically you upload the source code to the GPU. Then you compile. It's just like any CPU program. You write some source code, then you compile, then see if it succeeds or not. So So this is the stage. Basically, you check whether compile succeeded. If not, actually, you can call another function. Then you can get some information about why it fails compiling. Then it will indicate, give you some hints what's wrong with your program, with your shader source code. Then you can do some modification. So now we compile the shader, and then we need to load the program to the GPU so GPU can run and can render. So this is the source code how to build the program. So first, you need to create a program. That's very simple. Then we use the function in the previous page, the get shader. So we create shader and compile the shader. Then what we need to do is we need to let the program know this is the vertex shader you're supposed to use. So we say attach shader. Basically, we attach the vertex shader to the program. And then we do the same for the fragment shader. So now we have a program with one vertex shader, one fragment shader. So the program is complete. Now we can compile. We can link. It's just like the CPU program. We compile, then we link. Then after link, we check whether link succeeded or not. And again, here I didn't have this code, but if the link fails, then you can get some log information. Will tell you why it fails. Hopefully, the information is good enough so you can immediately know what's wrong with your program. So now we link the program. If it succeeded, we have a valid program to run on GPU. But we need to tell the GPU, this is the program you should use. So that's a line of code just doing that. Say use program. So set this program as the current program for the GPU. Then those lines is basically prepare the vertex attributes for later use. Because we know, as we see in the vertex shader, we have position, we have attribute position, we have attribute color, and the program is basically tell you what to do with those attributes. But again, then you need to link some data to the program. So say this is where you give the data to the GPU, and so those are the location. You get the location of those attributes. Then later you can bind vertex data to the vertex attribute location, and bind color data to the color vertex location. So that's what this is about. Give you the location, later you can binding data to them. So now we set up the GPU, we set up a program, set up shaders, and the next is we have the program, now we need the data, because there are two parts. One is program, what to do with the data. Now we need to get the data to the program so we can render the stuff on the screen. So the data here in WebGL is what we call the data buffer. So first we need to create a buffer and say this is bind buffer is basically saying this is the current buffer, and all the future operations on the buffers are made to this buffer until I bind another buffer as the current. So this is the buffer data for the triangle. It's quite simple. You can see it's XYZ and RGBA. It's seven floats for each vertex. Then we have 3 vertices, so we totally have 7 by 21 floats. That's the data we have. Then this buffer data is basically saying upload this data to the GPU. So now we have the data, we have the program, we have the program on the GPU, we have the data on the GPU, and then we need to only send a simple command to through WebGL, say, now draw something for me. That's the last missing part of this simple program. So viewport clear is basically say, this is the region I want to draw, and before I draw, clear the region first. Of course, you can set, here I didn't set the clear color. So basically use the default color to clear the scene, but you can actually say what kind of background color you want. Then you can say clear color, set up the color, then do the clear. Then you have a region with a given background color. So this is basically binding the data. The data is already on the GPU, and the program is also on the GPU. So now basically you need to connect the data, feed the data to the shader programs. So this is what exactly this is doing. So in the shader vertex program, we have two attributes. One is position, another is color. Here I also draw the surface normal, but in our program, we don't have normals. So we have positions, we have colors, and so those lines is basically just binding the data to the location. So you can see the program dot position attribute. So say bind those data to those position, and 3 is saying this is for position. So we have 3 data x, y, z, and the type is float. And false is basically normalized or not. You don't have to worry about that here. And stride is basically because for each vertex we have 7 floats. So we say basically for each vertex you jump another 7 floats to the next vertex. And 0 is because for the position we put position first, then color. So the last parameter is offset. So we say 0 is in those 7 floats, we read from 0, 1, 2 as x, y, z. And so the second example, the color, you see the offset is 3. So basically it's saying start from 3, 4, 5, 6 as RGBA. That's the offset. And the 4, because there's 4. 4 is basically saying the data is RGBA. It's 4 floats. The top is floats. And if you read the API, the meaning of all those parameters will be very clear. Now we have the data, we have the program, and we connect the data to the program. Then the last thing we need to do is say draw. So we draw a triangle and start from 0. 0 is sometimes if we have a large data and we only want to draw a part, so we can start from anywhere, draw only partial part of all the triangles. But here we only have 3, so we start from beginning, and the 3 is saying we have 3 vertices. So this is only one triangle. And that's all. This is all the code you need to draw a triangle. I mean, it's way more lines than just hello world in C or Java, but it's still very simple stuff. So any questions so far? Do you feel confident now you can call yourself a WebGL expert? When I started working for Google, I started from this example, so that's how I learned WebGL. And no matter how complicated the scene looks like, this is the foundation. You can do some physical simulation, all kind of stuff, but that's not related to graphics. The part to graphics is just this is the core. This is everything you need to know. Oh, actually, the only thing missing is the texture, how you deal with texture. But once you set, if you learn how to assign the texture to the triangle, that's everything you need to know about how to draw 3D graphics. So this is not bad. Actually, you can call yourself WebGL expert if you fully understand what this is about. So now I want to talk about, after the basics, I want to talk about a little bit about how to make good WebGL applications. So here are some rules. Because WebGL is fundamentally graphics library OpenGL, so whatever rules for OpenGL to make it good, it also applies here. So first, basically we need to minimize a few things. First, try to minimize the draw cost. So for example, if you want to draw a million triangles, you can combine all the triangles, say draw and draw a million triangle. Or instead, you can make a million draw costs each time you just draw one triangle. And the latter case is extremely bad. So basically, you try to combine your geometry and try to make a single draw call. That's the best. But if you cannot, or if that's too complicated for you to manage the data, for example, you have a human, a dog, then you will have to make 2 calls. That's fine. But if you make a million call for a million triangle, that's not good for WebGL. And then you also try to minimize the binding of buffers texture program. So basically, as I showed before, if you say bind buffer, basically you set the buffer as the current, then all the future operations is applied to that buffer until you say bind buffer again. So basically, you try to make as minimal as possible the switch between buffers, between textures. So basically, if you want to do something for one buffer, you bind this buffer and do them all, then you switch to the next buffer. Instead of you do something here, switch to another buffer, then switch back. This will make the WebGL performance bad. And the same is uniform variables, which I didn't explain what it is here. And also, there are state switches, just like enabling, for example, depth testing and enable vertex attributes, those kind of things. Basically, make sure you know what you want, what do you have to do. Then basically make as minimal state switch as possible. That's will make your OpenGL, WebGL performance pretty good. And then for WebGL, because WebGL is JavaScript plus shader, so JavaScript is running on CPU, and the shader runs on GPU. So basically, for browsers, you try to offload as much work to GPU as possible. So then on the CPU side, it can be very fast, very smooth, because CPU will handle all the user interaction. Like user wants to click, play games, interact with the scene, all those kind of things is happening on CPU. So if you do tons of WebGL stuff on the CPU side, that will be bad. But if you offload them to GPU, then the CPU side can be saved to do all the browser UI and browser stuff. So that's the WebGL big rule. The second is, because what I showed before is just example, just draw something. But many times to make an application interesting, you have to interact with the scene. So you have to, for example, you have to click, pick. Pick is a common interaction between user and the game, because, for example, you click on the screen, then basically the program needs to tell you, did you click on the object or did you click on the thing? That's picking. So in the early days, we have Google Body, which is basically it has a human body and with different organs and different bones, with names and with information, and it's all built in WebGL. And then you can click on a part of the body, then it will tell you some information about it. Unfortunately, this Google Body is no longer available from Google, but the technique they used in Google Body is still pretty amazing. So, because one Google Body has about 1 million triangles, and still you can achieve real-time interaction. You can rotate, you can pick in real time. So this is how WebGL can do, what's the performance can be like. And the selection, basically you click, then the program needs to tell which part you click, because there's a million triangle on the scene, so you have to do something wise. Otherwise, if you just try to compute whether this click interact with a million triangle, that's going to take forever to finish. So one technique which is not used by Google Body is you can do ray tracing. Basically, your click is like you shoot a ray to the scene, then you can compute how this ray is interact with all the triangles, which triangle interact first, which interact next. Then the triangle closest to you will be the triangle you hit. That's the general technique you use in graphics to decide which thing you hit through a click. And of course, you can do some optimization, like you can do bounding box, so detect whether the ray hits this part of the body can be fast, because if it's outside the box, then you don't have to compare with each triangle inside the box. But still, this is still a lot of mathematics going on the JavaScript side, because like the body can be rotated. So the bounding box also, you have to also apply all the transformation to the geometry and everything, and for each click. So those are a lot of math on the CPU side. And so what we want to do is we want to offload those kind of computation to GPU side. So the CPU side can save it for something else. Yes.
What if you upload it to the server instead? Lots of input data to pass.
Yeah, you can do it on the server side if you are willing to provide a service like that. But it will be pretty heavy GPU. Right. Most currently most servers are more CPU heavy. And do they even have a GPU for? Yeah. Yeah. So basically, you are doing GPU work on CPU in the server, which may not be very fast. Right now, I know some game companies, they are using web-based gaming, so they provide the servers to do rendering, but I don't know how well they are. But this is definitely could be a future option. So what we do is, in Google Body, what we do is how we use GPU to decide which body part you select is when we load the body, load the model, we say this is the heart, this is the kidney. Each part we assign different color. Then we draw the body not on the screen, but in an off-screen frame buffer. In an off-screen canvas, we draw it with those colors instead of with like lighting, with real texture, but we draw it with those assigned colors. So then what you see is something like this on the left side. So basically, this is just a 2D canvas with a bunch of pixels with different colors. Then when you mouse click, you decide which pixel you click. Then this pixel will be corresponding to which organ you click. And this is how you do picking through GPU. You render different parts with different color. Then based on which color you get, then you can know which body part you pick. And of course, you can do it on different scales. For example, if you want to select a triangle instead of a heart, then basically you assign color to different triangles. Then based on the color, then you can know which triangle you get. So I think this is a very smart trick to do, and which allows you to interact with 1 million triangles in the real time. And it's proved to be very effective because Google Body is already launched before, and people can interact with it no problem. So then I want to talk a little bit about particle system. This is one demo of particle system. So here's another example, different kind of particles So each particle will have is moving around according to time. As time passes by, each particle will be moving. So what we can do, there are two ways again. One way is we can check the position of the particle in JavaScript. Basically, at each time frame, we can compute the position of each particle. Then the GPU is only to render, is only to draw that particle in the given position. But again, in this demo, what we do is we put all the computation, the motion, equation, everything, evaluation to the GPU side. Okay, so the demo, the second demo I show, it animates about 2,000 particles at 60 frames per second, and the animation mathematics is done on GPU. So here's how it's implemented. So each particle, the motion, the current position is defined by a set of parameters. And those parameters including initial position, velocity, acceleration, and spin. And those parameters are set up in the initialization time. So they can be offloaded to the GPU. And then at each frame, there's another parameter we need to provide, which is the time. So on the Vertex Shader, basically we can apply the mathematics for the motion equation. Then we can, based on the time given at each frame, then we will know what's the exact position of each vertex, and that's how we can get the particle system to work at 60 frames per second, because the GPU is doing most of the computation instead of CPU. So then there's physical simulation, and here's one cool demo I like very much. Bad, because I switched again. This is the water tank. You can see the lighting and everything. I wish this is done by me, but no, it's someone else. This is really cool demo. Oh yeah. That's what you can do with WebGL. Yeah, it's rendered live. How do I? How to make it jump? Oh, I have to manually jump it. Okay, so yeah. So that's the kind of stuff you can do with. I'll just stick with this instead of bringing it up, so I have to go through all the slides again. So physical simulation can also be done on GPU, and so basically we need to store the state of the physical simulation on the GPU. Then the property, whether we can do it on GPU or not, depends on if each step of computation relies on the nearby neighbors. Because if each simulation of each, it's a global thing, then because GPU is supposed to be parallel computation, so if it's very global, then you cannot utilize the property, the parallelism of GPU, then it may not be fast. So that's one property. It relies only on the nearby neighbors. So if you have a simulation like this, then maybe you can think of a way to simulate the physics using GPU. And of course, to do physical simulation, you need to you need accuracy. So floating point textures, which is very important in those physical simulation. They are not the core part of WebGL, but they are provided through WebGL extensions. And I think it's already implemented in both Chrome and Firefox. So there are several other examples, and this is a link. You can check a few other cool demos out. So here is the part I show you in the beginning of the talk is the non-photorealistic rendering. So now let me explain what these a few lines of magic code do. Those lines basically change the rendering from a shiny teapot to a cartoon style. As you can see, the first line is basically, this is actually not exactly intensity of the color, because this basically I just take the norm 2 of the color. But basically this will give you a rough idea of how bright this color is. Then I say compare this value with threshold. If it's larger than 0.95, that means this color is very bright. So I use the highlight color, which is white, which is close to white here. Then if it's in the middle, then I use the bright color. But if it's really low, this brightness is really low, then I use the dark color. So basically you are segmenting the colors into 3 parts, and then you transform those continuous color realm into only 3 colors. That's what the first example I show you is about. Yeah, basically, if you comment those lines, then you see a shiny spot. But if you add those lines, that's processed on a per pixel basis. Basically, you already compute a pixel, then you just do some post operation on them, then you get those kind of cartoon style rendering results. And here's another example. So you can choose how many tones you want, 2 or 3 or even 8. Then you can pick colors and everything. And this is done by my colleague Greg. So this is another example of what kind of cool things you can do with WebGL. So here is some basically what I do is basically, if regular rendering is basically you compute the color of the current pixel, and then you just set it. And for the non-photorealistic rendering is you compute the color, but before you send it to the GL frag color, then basically you do some conditioning. If it's bright, then use a brighter color. If it's dark, then using a darker color. That's how you segment the results into 2 shades. So last, I want to show you some resources you can find if you are going to explore more about WebGL. And there are many libraries already exists and make it much easier to build WebGL applications. And here are a few recommendations. Then here are some talks and demos you can find online, which will give you. So today what I talk is really the basic of WebGL, and there are more advanced techniques that you can use to build complicated WebGL demos, and you can check out Greg's talk and a few other talks. And these Chrome experiments provides tons of very cool WebGL demos. Then this is the WebGL official wiki page on the Chronos. And then there's public WebGL mailing list, which is basically discussing about WebGL spec. For example, if you try to develop something and you realize it's not possible or it's very inconvenient with the current spec, then if you have some idea, then you can propose the stuff on those lists. And the last list is the developers list is you can advertise what you have done, or if you're a newbie to WebGL, you can ask questions, or even if from time to time, I see people just post a segment of code and ask what's wrong with my code, and there's always very, very nice people to help you out. So those are the very useful resources. Then, of course, this is web API. So the fundamental, the ultimate resource of WebGL is the web, because whatever cool WebGL demo you see, their source code is available to you. It's not like C++ or Java. They compile, then you cannot see what's going on. In JavaScript, the beauty of JavaScript is whatever they do, it's available. You can just click tools and view source, then you can see everything. Of course, some people will do some post-processing, make the variable like weird names, or make the lines all come together, make it very difficult to read. But if you have patience, you still can understand what they are doing. And that's the beauty of the web. Yeah, so there's one last example I want to show. I think that's the trademark example demo for WebGL in the very beginning. That's the fish tank. And you can select how many fishes you want. And then you can see the frame rate per second. But for me, this is a pretty, not a very good GPU. It's only a low-end Intel, but it's already with such a large thing, it's still pretty good frame rate. Okay, so basically the idea of WebGL is supposed to make your program run anywhere the same behavior. So that's why we choose OpenGL ES 2.0 as the foundation of WebGL instead of more advanced OpenGL, or more like more OpenGL with like more core features. That's because we try to make the experience the same. So as for your question, right now we don't have a benchmark built in with the browser, so we don't know how fast the rendering is. We only know that hopefully if we allow the WebGL to run on a certain GPU, on certain driver, at least they render correctly. That's what we can guarantee. But for the speed, right now, we don't have a mechanism to say this will be on 30 frames per second guaranteed. We don't have that. What you can do is, like Maps.gl, before they start, like the Google map, they have a version of WebGL map called Maps.gl. What they do is, before they launch Maps.gl, they run a few small benchmark to gather the speed, a few features, a few measurements they want from you. And if it's really bad, then maybe they will not even run. So that's currently how people do things. But I think we are trying to do something on the browser side. So see if we can provide some pre-computed evaluation of the GPU performance. So then maybe you don't have to build benchmarks on your own and run it before user launches it. Basically, you can just query the browser, say how fast the GPU is, and hopefully, we already run it when when the browser is idle. We don't have to wait until you launch the GPU, but launch your application. But beforehand, when the user is not doing anything, we already run the benchmark and collect the data. So when you query, it will be immediately available, telling you how well your GPU is, how good it is. Then then you can decide what you want to do, whether you want to run or not even launch. Or sometimes people have fallback if the 3D graphics is not good enough. Maybe they have a CPU side implementation, so basically use the CPU. Or even, for example, like Angry Bird, they have a WebGL version and they have a 2D canvas version, because for the Angry Bird, it's basically not much 3D, so they can also do it in Canvas 2D. So then maybe those kind of fallback solution. So, but that's in the future. Not right now. It's not available. Okay, that's a very good question. So the question is, do we have a standard to send 3D data for the WebGL application? The answer is no. Currently, we don't have such a standards. So it is up to the developers to define their own standards. But we do have, like, if you want to use some standard, like, for example, CRADA, then if you search the web, you can find available tools for you to send and for you to interpret and unpack those kind of data and make it more convenient for you to use. Okay, thank you very much for your time, and now let's enjoy lunch.